Welcome to the Walton Pi. Today we're going to talk about what exactly an inner product is. Now before we get started, if you haven't already, please consider subscribing because it really helps me to keep making these videos. Okay, so an inner product is a very special type of a function that's going to take two inputs and then either return a real number or a complex number. And it is usually written like so, angle x comma y and then an angle going the other direction. So a real inner product, that's a function that's going to be returning a real number, and as we might expect, a complex inner product will be returning a complex number. So a real inner product is a function that takes two inputs x and y and returns a real number that satisfies the following three properties. First, the inner product of x and y is the same as the inner product of y and x for all x and y. So this is what's called symmetry. Then we have the inner product of ax plus by and z that's equal to a times the inner product of x and z plus b times the inner product of y and z for all scalars a and b and for all x, y, and z in whatever we're taking inner products of. And this is called linearity in the first argument because this is linear only looking at the pieces in the first section of our inner product. And then the last one is what's called positive definiteness, which means that if x is not 0, then the inner product of x and x has to be bigger than 0. A complex inner product is a function x and y that takes two inputs and will return a complex number that satisfies the following properties. Now these are almost the same as the last one, but there's a couple subtle things that we have to pay attention for. The first one is that the inner product of x and y is equal to the complex conjugate of the inner product of y and x. This is called conjugate symmetry. So this does not mean that inner product of x and y is equal to the inner product of y and x, but they are related through complex conjugates. Next, it is still linear in the first argument, so that piece doesn't change. But whereas a real inner product can be linear in the second argument, for this one, it's not going to be linear in the second argument as well. Now, the last one is that if x is not 0, then the inner product of x and x is bigger than 0. This one's a little bit confusing because complex numbers are not always bigger than 0. That is only true for real numbers because complex numbers do not have a definite order. However, if you take the inner product of x and x, that will always give us a real number, and so that means that we are going to be able to say that the inner product of x and x has to be bigger than 0. Okay, the following are going to be true no matter what inner product we're dealing with. The inner product of x and 0 is the same as the inner product of 0 and x, and both of those are equal to 0. Next, the inner product of x and x is always real and non-negative. Now we can see this by going back here and looking at the conjugate symmetry argument. The inner product of x and x, if we switch the order, that means that that has to be equal to the complex conjugate of x and x, which means that the number is equal to its own complex conjugate, which means that it has to be real. And then the last property is going to say it has to be non-negative, where 0, 0, the inner product of those two, that's always 0. So that's why we have this being true. Next, inner product of x and x is 0 exactly when x is 0. That means that's the only thing that's going to have x comma x in the inner product be 0. And then this is our linearity-ish argument in our second piece. Now what this is called is, since this isn't perfect linearity, it's almost linear but it's not quite. This is what makes it a sesquilinear form. Sesqui meaning 1.5. It's almost linear but not quite. Okay, now let's talk about some examples of inner products. So first and most common example is the dot product. So x comma y dotted with a comma b when we're dealing with vectors, that'll be xa plus yb. This is an inner product. Another one is if you're dealing with complex numbers, this is an inner product that you can apply to the complex numbers. So the inner product of two complex numbers x and y, that's just x times the complex conjugate of y. That is an example of a complex inner product. And then if you're dealing with real numbers, then just taking x times y, that is a real inner product. I hope this video was helpful in understanding what inner products are as well as their definition, as well as maybe seeing a couple examples that are fairly simple, not nearly as complicated as some of the others that you can get. But hopefully this was helpful, and I hope you enjoyed it, and if you did, please consider liking and subscribing. I hope you have a great rest of your day, and good luck with all of your math.